Okay, so let's begin. So okay. So the ripple ladder and the ripple subtractor. Okay, so what this basically does is that when you have a multi-bit forming a multi-bit addition, we said that the other basically takes three inputs, right? So your first input, the full adder takes three inputs. So your first input, your second input, and then your third input, which is usually the carry in. Okay. So when you have, let's say, a complex addition to perform, like let's say 1011 plus, let's say 11, and you are performing this addition here. A ripple ladder is needed to perform an addition like this. So we know that every process of the ripple ladder is basically that of two. And so usually if you have this kind of operations, NB triple ladder is needed to perform this kind of operation. Please, sorry, I think I had a network disruption. Okay. So the number of bit determines the type of ripple ladder that you are going to need. Okay. So for an operation like this, you are going to need a 4-bit ripple ladder, because if you check from the first number, which is 1011, it contains 4 bits. Okay. So the second one, though, is just 2 bits, but I fill the rest of the bits with zeros. Okay, which now makes it 4 bits now. So you can progress to perform So yeah, so I was earlier indicating that we said we had 1011, right? So the second one is 11. So we are going to fill the rest of the bits with zeros. So in this case, the last bit here becomes our so this here becomes uh, our A here, then this bit becomes our B, okay? So repeat the same thing for the rest. A1, B1, etc., etc. So you just repeat this set of inputs for that. So here it becomes A2, B2. Here becomes A3, B3. Okay. So in just the order that is arranged here. So you can already see that. So what we do is that we perform the addition using an n-bit triple ladder, where your n represents the number of bits in the addition that you are performing. In this case, you have 4 bits, right? So here you are going to use a 4-bit triple adder. So what you are going to use is that each full adder will perform one of the addition processes. So we have 4 different additions to be performed, which is 1 and 1. We have 1 and 1 again. We have 0 and 0, and we have 1 and 0. So here your B0 is going to be 1. Your A0 is going to be 1. Okay, so I'm coming. And then here your A1 is 1, your B1 is 1. You've already labeled it right. So your A2 is 0, your B2 is 1, and here your A3 is 1, and then your B3 is 0. So this is how the addition will be performed via a 4-bit triple adder. Okay, and then we are going to accept our carry in from our previous operation as a valid input. And then we forward our carry out to the next operation as an input, okay, as our third input. So when you start, or for the first operation to be performed, that is at 1 and 1, we don't have any carry, or we don't take in any carry, because that's the first operation to be performed. So we assume that the carry is null. So for this place, the carry is null. But then 1 and 1 gives us 1 and 1. What are you going to get if you are performing this addition? That gives us, I believe, we have 0 and then a carry of 1, right? So we are going to have a carry in of 1, which we are going to carry out as at this point. So if you carry out 1 here, we are going to get a carry in of 1. It means that when we are performing this addition here, we already have a carry in of 1 already. So this is going to be 1 plus 1 plus 1, which is going to give you another 1 carry out. So here will be the sum. So then you record the 0 here, okay, and then you record a carry here. So here is going to be 1, a carry out of 1. Then we have 0 plus 1 plus 1. That gives you 0 and a carry out of 1, which later serves as a carry in here. And then you have 1 plus 0 plus 1. That is going to give you 1, right? And a carry out of 1. I believe we can all see that, right? So this is how such an operation is going to be, such an addition operation is going to be performed. And the final addition is going to be in the form your S0. So you are going to have this is going to be our sum operation here using the ripple, a 4-bit ripple ladder. Okay, so we are going to get, let me just draw this right here. So we are going to have S0, S1, S2, and then we'll have our X3, and then our last C out, okay, as our last carry. Okay, so we are going to, this is how our output is going to look like. So to represent that output with what we have, we know the last carry is 1. So we have 1, and then our S3 is 1. Then our S2 is 0. Our S1 is 1, and our S0 is 0. Okay, so that is, or that will be how that addition operation would have been performed using a 4-bit ripple adder. Okay, so now let's move on. And then a ripple subtractor also works in that same manner. Okay, but then with that one, we don't use carry out. We said that with a subtractor, we rather use borrow in and then borrow out instead of carry in and carry out. So let's just recall that. So today we're going to look at comparators and then how they work. And then after that, we solve some questions under comparators and then we are done with that. All right, so a comparator. So when you are talking about comparators, as the name suggests, comparators are just used to compare numbers, or we use this to perform comparison operations, or we use this to perform comparisons. Okay, that is what we use our comparators for. So let's say, assuming we have n number of bits, or assuming we have let's say our n is 2. So assuming we have a binary operation with 2 bits, what our comparator is going to do is that our comparator is just going to compare the number of bits available. Okay, so 2 bits is going to look like, let's say, 1 and 0. Okay, this 2 bits here. So let's say we have 1 and 0, and then let's say 1 and 1. So the job of our comparator is to compare these two things here, whether one is less than the other, is equal to the other, or is greater than the other. So these are the 3 basic comparations that our magnitude comparator does. Another name for the magnitude comparator is also the digital comparator. Okay, so anywhere you see the name a digital comparator, it means the same as your magnitude comparator. So let me move to a whiteboard. Please, can you all see the plain sheet? Please, can you all see the plain sheet? All right. So let's move to a plain sheet and start with the 1-bit magnitude comparator. So what you are going to do is that you look at the definition, and from the definition, you look at the block diagram, and from the block diagram, you look at the truth table, and after the truth table, you look at the logic expression, and after the logic expression, you look at the logic gate diagram. So after you are done with this, then we can say you are done with the 1-bit comparator, and then you look at the 2-bit comparator also. So now let's look at the 1-bit comparator, the definition. The definition. So what your 1-bit comparator does is that your 1-bit comparator basically compares two 1-bit binary numbers. Okay, so let's say it takes 2 inputs in a form of A and B, each comprising of just 1-bit binary numbers. So your A can only be 0 and 1 when you are dealing with 1-bit comparator. Your A can be 0 or 1. Your B can also be 0 or 1. Okay, so each value can be 1 bit per time. It can't be 2 bits. For example, if you have A being 0, 0 and B being, let's say, 0, 1, this isn't a 1-bit comparator. This is a 2-bit comparator, because if you count, you can see that here you have 1 bit, then you have your second bit right here. Each operation, you can see you have your 1 bit, then you have the 2 bits right here. Okay. So this right here is our 2-bit binary numbers. And if you want to perform a comparison for this, you don't use your 1-bit comparator. You rather use your 2-bit comparator to perform that operation. But then since this one here has only 1 bit, you can use your 1-bit comparator to perform your comparison. Okay. And then with the comparator, the definition we give for the comparator is that it is used to compare n number of bits. All right. And then its output is always the same. Its output is always either A equals B, which is equality. Either A is greater than B or A is less than C. These are the 3 possible outputs that a comparator can return. So any other output apart from these 3 is simply not coming for a comparator. Okay, the reason why it is important that you understand some of these things is because of our mode of examination, which is through objectives. So any little detail can be a question on its own. So if you are giving something like, let's say, A minus B is not a comparison, okay? Or with A minus B, you are not performing anything, you are subtracting, which is a subtraction operation, not a comparison operation. So for us to term an operation as one that can be performed by a magnitude operator, it should be one which is targeting either equality, which is targeting to establish which is greater or which one is lesser. These are the 3 basic operations that our magnitude comparator can perform, or is meant to perform by definition. I believe we are all okay with that. All right. So based on this definition, we can have only 2 sets of 2 inputs for a 1-bit comparator. And to understand how this works, we use a relationship, okay? And the relationship we use is 2 to the power n to establish the number of inputs, okay? So where n is your number of bits, so n is equal to number of bits in that particular comparator. So n is your number of bits. So 2 raised to the power n will give you the number of inputs or number of variables involved. And then we use our second expression is 2 raised to the power 2n tells us the number of rows that we are going to use in our truth tables. Please, are we together? So this 2 raised to the power n tells us the number of inputs, the number of input variables that we are going to use. And the number, and 2 raised to the power 2n tells us the number of rows that we are going to use in our truth table. So for instance, if you have a 1-bit comparator, in order to know the number of distinct input variables, we use 2 raised to the power 1, which uses 2. Okay, so from this, we know that our comparator is going to use only 2 variables, which is A and B. But assuming we have a 2-bit comparator, we are going to have 2 raised to the power 2, right? Which gives us 4. So we should know that the number of distinct variables we are going to use are 4, which is A0, B0, and then A1, B1, or you can decide to label it as A0, A1. So A0, A1, then we have A0, A1, then we have B0, B1. Okay, so you can see we have 4 distinct variables right here. Please, are we together on this? How we use it? 2 to the power 2n. So we use 2 to the power n to denote our number of inputs, and 2 to the power 2n to denote the number of rows or possible combinations we are going to have as inputs in our truth table. Please, are you all okay with this? Does anyone have a question? Or is there any confusion we need to clarify before we just kind of voice it out? Please, are we all okay so far? All right. All right, so let's move on. So now let's establish a very, very, very important point here. Okay. So our comparator, no matter how many number of distinct input variables you are going to have, that is, let's say if you have a 3-bit comparator, for example, a 3-bit comparator is going to look quite complex, because if you use 2 raised to the power 3, you are going to get 8, right? And 8, we can write it in the form, let me see. So 8, we can write it in the form A. So we can have A0, we can have A1, we can have B1, okay. No, we can have A2, I mean A2, then we just proceed with, I mean A here, A2, then repeat same for B, okay, for that. But then you realize that, let me rather use 2 for reference, okay, so that we don't get confused. So with a 2-bit, we are going to have, let's say, A0, A1, and then B0, B1. So with this, if you are performing a comparison, what we do is that your magnitude comparator, by definition, only compares A and B, because we said that our output can only be, regardless of the number of bit comparator that we are using here, our output can only be A equals B, A is less than B, and A is greater than B. So we can see that it only compares A and B. So there is no room for, let's say, A0, A1, B0, B1. So it means that regardless of the inputs that the distinct input variables that you have to run it down to A and B. Okay, so let's say A0, A1 is, let's say, 0, 1. B0, B1 is, let's say, 1, 1. These are 4 bits here. So to perform the comparison, the first 2 bits will be grouped as 1. And the second 2 bits will also be grouped as 1. So the first 2 bits will be our A, then the second 2 bits is going to be our B. And now we can perform the comparison. So instead of just comparing 0 to 1 or etc., we compare 0, 1 to 1, 1 instead. Please, I don't know if you are getting what you are referring to. So we'll group A0, A1, and then label it as A. And then B0, B1, and label it as B. That is how the comparator works. So it groups its inputs that is given into 2 sets of inputs before it does its comparisons, okay? So the first group will be named A, the second group will be named B. And then it would compare and return the output A equals B, A less than B, and A greater than B. So at every point in time, let's establish this fact here, and this is very, very important. At every point in time, a comparator is only going to use one comparator for its comparison. And that comparator can only be equal to, less than, or greater than. It can only be one of the 3 per time. Okay. So if you should have a question that should ask that, oh, maybe how many comparator does a magnitude comparator use at a time for its comparison? It's just 1. So at every point in time, it can only use an equal to sign, less than or greater than, one of this per time. because it would group its inputs and then compare them using one of these three per time. Okay. So I believe we are okay. All right, so let's move on to the block diagram. So based on all that we've said, we know that a comparator will take two inputs. So we have our A, we have our B. So let's call this magnitude comparator. And then it's always going to return three outputs. Your first output is going to be for equality A equals B. Your second output is going to be A greater than B. And your third output is going to be A less than B. So at every point in time, a magnitude comparator will take two inputs and then return three outputs. And this is our block diagram. For our magnitude comparator. All right, so we've already spoken about the types of magnitude comparator. I said we have 1-bit magnitude comparator, we have 2-bit magnitude comparator, etc., etc. So now let us look at the truth table for a 1-bit magnitude comparator. We said that a 1-bit magnitude comparator takes two inputs, which is A and B, right? So we have A as our first input, B as our second input. And with these two inputs, we are going to have an output of A equals B. Then we have A greater than B. We have A less than B. So you said these are the three outputs you can have, right? And these are the two inputs that you can have. So in order to know the number of rows, we use the formula 2 raised to the power 2n, right? So in this case, our n is 1 because we have 1-bit comparator. So that gives us 2 raised to the power 2, which is 4. So you know we are going to have 4 different rows here, right? So the first is going to be 0, 0. We all know how this is done, right? So we have 0, 1, 0, 1. And then we have 0, 0, 1, 1. This gives us our 4 inputs for our magnitude comparator. And then this is the rule for magnitude operators where we are determining the outputs. Okay, so when you are dealing with equality checks whether two inputs are equal. So if two inputs are equal, you return a high for A equals B. Here is the case. At every point in time or at any comparison, a magnitude comparator can only represent a high for one symbol and all others will be 0. So for instance, if this line of comparison, if equality is high, then everything else will be zeros, okay? And then 0 and 1, is 0 equal to 1? Is 0 less than 1 or 0 is greater than 1? Please, can someone help us? So yeah, which one is going to be high here? Hello.
Hello, sir. Please, we are here.
Okay. So I was asking that a magnitude comparator does compares your inputs, and whichever case is true, it returns a 1 for that, and all others is 0. So you have 0, 0. We said 0 is equal to 0. So for equality, we put a 1 right there. So when we come to the next line, we have 0 and 1. So we have to perform our comparison. So is 0 less than 1? 0 is equal to 1, or 0 is greater than 1?
Okay, so I think 0, 1, that's A equal to B. The answer there will be 0. Then when we come to A greater than B, the answer there will be 0. Then we come to A less than B, the answer there will be 1.
1, which is very true. Because you know that 0 is lesser than 1. So we are going to have a 1 only as A is less than B. And we know that for magnitude operators, for any possible set of inputs, only one comparator can be true or can be high. The rest will be 0. So immediately you're able to determine the one which is high, then all others are going to be null, or you are going to put 0 for all others. So 1 and 0, we just have to also determine which one is going to be high, and then the rest will be 0. So we know 1 is greater than 0. So we know this is going to be 1. And then everything else is going to take 0. And then 1 and 1, we know this is equality, right? 1 is equal to 1. So for our equality, we are going to put 1, and the rest will automatically take 0. So now we have our truth table for 1-bit magnitude comparator. Now let us look at our logic expression. So to look at our logic expression, we have to be able to understand some basic relationships here. If we're able to have that understanding straightforward, then we are good to go. We do it separately. So you have to first determine your expression for A equals B, and then determine your expression for A less than B, and then that of A greater than B as well. Now, I'm going to teach you a very short method to do it. If you are not able to get this short method, usually you might have to, okay, I think for 1-bit comparator, they're straightforward. But when you get to 2-bit comparator, I'm going to teach you a short method that you can use, that you can be able to determine your logical expression or your output without even going through the hassle of drawing your truth table and stuff. Because look, for the sake of examination, we are doing MCQs and we are dealing with time. So if you have a question on the magnitude comparators, I'm not sure that it will be ideal to now start drawing your truth tables for 2-bit comparator, which will be a very long process. By the time you are done with that, you would have spent maybe 15 minutes or 10 minutes just working on that alone, okay, or just working on one question. So that method is advised for that scenario. And then when you get there, I'm going to show you. Okay. So when you get to A equals B, we said just as we did for full adder, half adder, etc. We look at our outputs with output value of 1, right? Those are the only ones we are interested in. The zeros, we don't need them. So for our first one, we know A is 0, B is 0. So if A is 0 and B is 0, do we write AB or A complements B complements? Can someone help us out?
Write A complement, B complement.
All right, so A complements or A bar, B bar for that. Okay, so and then we also have a 1 here, right? So this is 1 and 1. So that's 2. What are you going to write?
That one will be AB.
Okay, that one is going to be AB. Okay, and I'm sure we all already know what this means, right? we said that initially when we're looking at full adder, half adder, we establish a concept that if you have AB plus AB, and then this A is bar, and then here the other side, this B is bar. This is an XO expression here. So this is A XO B. But if you have the same AB plus AB, and one side has bar and a bar, and the other side doesn't have, this is an X null, which is exclusive null. Okay, so we are going to have A X null B. So let's just familiarize ourselves with this relationship, because it is mostly used, or it's mostly evidence around this topics. Okay, so this particular expression here, you all know what it's going to give us, right? It's going to give us A X null B, right? That is what this is going to give us. Are you all okay with this?
Yeah.
Okay. So another way, or a very easy way that we could have just arrived at this without going through the hassle of checking our truth table, is that, look, the equality rule says this. The equality rule is saying that we can only obtain equality, okay, or we can only say A and B is equal only when the two inputs are equal, right? So our input is A and B. So we only know that our equality here will be high, because you can see that when the two inputs are high, that is A0 and 0 is 1. When our two inputs are equal, I mean, our A equals B becomes high, right? So if A is 0 and 0, A equals B will be 1. If A is 1 and 1, A equals B is 1, right? So this gives us a general rule that always, when the two inputs are equal, A equals B is going to be 1. Please, do you all agree with that? That when our two inputs are equal, A equals B is always going to be 1. But you can see that A equals B was 1 here. Check the input. You can see that the two inputs were equal. A equals B was 1 here. If you check the input, you realize that the two inputs were equal. So the general rule for A equals B is that your two inputs has to be equal, because you are comparing the two inputs to know whether they are equal or not. And if they are equal, you put a 1 for them. Okay. And when you are deducing your logic expression, you basically look for the ones that are only 1, which satisfies the A equals B criteria. So here we can just, if you are applying propositional logic, okay, we can say that whenever we have our input A being equal to our input B, the output value is 1, okay? And I think at this point, you are familiar with the fact that whenever you have A equals B, A equality always will result in an X NOR gate. That is the same as A X NOR B. Please, this is a very, very general concept that we have to be able to establish here. Because if you have A equals B, just deduce your logic expression, perform the minimization, and it will always be A X NOR B. Okay, so whenever you have equality, the resulting Boolean expression is going to be an X NOR expression of your inputs. Please, are we together on this? But I wouldn't really hit much on that. Okay. So let us move to A is greater than B. So A is greater than B is only true when your first input is greater than your second input, right? So you can see that here our first input is 1, our second input is 0. And you can all establish that 1 is greater than 0, right? So here we did put a 1 there as at that point. So that is a point where we consider, okay? So that is a point where we consider. So we have our A being 1 and our B being 0, right? So we have A is 1, our B is 0. So please, what is that going to be? In terms of A and B, what is the expression going to be? If A is 1 and B is 0. Are you together? Monica, are you there? We've not heard your voice today. So A is greater than B. We can see that we only have a 1 when A is 1 and B is 0, right? So if A is 1, that gives us an A. And if B is 0, that is B prime, right? So that is the expression for A is greater than B. That's our expression for A is greater than B. Okay. And then if we come and take A is less than B, let's check this from the diagram. We know that is the third section, right? And it's only 1 when our input is 0 and 1. When our A is 0 and our B is 1. So if we come down here, we are going to realize that when our A is 0, that is A prime or A bar. And if our B is 1, that is B. So this is going to be our expression for A is less than B. Please, did we all get that?
Yes, sir. Yes, sir.
Okay. So now that we've been able to reduce our expressions, we can proceed to draw our logic. We can proceed to draw our logic gate diagram. Okay. But before we draw our logic gate diagram, I want to simply highlight another way we can reduce that without drawing our logic table. Okay. Our truth table. I mean, this is for the sake of examination. You know that in the case of exams, we are working with MCQs and we have very limited time. You cannot say you are drawing your truth table for everything and then make your deductions from them. It's going to take you a lot of time to be able to do that. So we can use this method to deduce our answer. And this is a very, very short method. Once you understand it, you'll be okay. Even if they give you 5-bit magnitude comparators, you'll be cool with it, or you can be able to apply the same method to solve those kind of problems. A second. All right, sorry. So let me explain how this method works. Okay. So if we take A equals B, all right, we all know that from a 1-bit comparator, we only have 1-bit inputs, right? So we are comparing two inputs, which are A and B. Okay, we are comparing two inputs, which are A and B. So now let's ask ourselves the question, a very simple question, that when will our output be 1 for A equals B? our output is going to be 1 for A equals B when A is 0 and then B is 0, or when A is 1 and B is 1. This is something very simple to deduce, because we know that any other scenario, if we take 0 and 1, this will not be equal. If you take 1 and 0, 1 and 0 is not equal. You cannot tell me that 1 and 0 are the same. 0 and 1 is not the same. Okay, but then if you have 0 and 0, 0 is the same. So it satisfies equality. 1 and 1 is also the same. It satisfies equality. Now let us all analyze very well. Is there any other scenario where you can be able to get equality under a 1-bit comparator, or when you are comparing 1-bit binary numbers? No, it's not possible. Okay, so these are the only two scenarios that checks or that returns an output value of 1. That is when A is 0 and B is 0, or when A is 1 and B is 1. Now we know that when A is 0 and B is 0, A is 0 is A prime, B is 0 is B prime. And we all know that our OR is addition, or our OR is an AND gate, right? And then our OR is an OR gate, sorry, which we write it as plus. And then we have 1 and 1. 1 and 1 is A, B, which gives you the expression A prime, B prime plus AB. And you all know that this thing here is the same as an OR gate, which is an XNOR gate, which is A, XNOR B. Please, can you all see that? And if you want to draw the logic gate diagram for this, you are going to have an XNOR gate, an exclusive NOR, which is this. Then we put ours. Oh, what am I doing? Please forgive me. So we are going to have this right here. And then we put our NOT symbol in front. And we put this here. And then we have this right here. Then we have our A, B. And the output is AX no B, which is A, B, and then our line on top. Please, can we all see that? Please, can we all see that?
Yes, sir.
Exactly. So this is how we can make or be able to deduce our logic expression for equality without even drawing our truth table. We just have to determine the scenarios where our output is going to be equal, or our output is going to be 1. That is when the two inputs are going to be equal. And this is very, very easy to do. You just have to determine all the scenarios where A and B will be equal. And you know you have only two input values, 0 and 1. So 0 and 1, you know A and B can be equal if A is 0 and B is 0, or if A is 1 and B is 1. You know A, 0 and 0 will be A prime, B prime, or it's plus A, 1 and 1 is A and B. That's all. All right. Or if I were to be you, I can even apply a very, very simple concept. And this is a concept that I'm talking about. If you have A equals B, if you have A equals B, you don't even have to worry yourself at all. If you are to draw this on a referencing, if you are to represent this on a K-map, you are going to get A, B, this here, this right here. If you are to represent this on a K-map, you are going to get this thing right here, 1 and 1 here. And if you are to try to minimize, it would return the same thing here. So I was explaining the last time we were doing, I think, full adder, half adder, is that there's a general rule that if you have, let's say, your ones aligned diagonally, okay, such that they can't be selected, or such that you can't, as in, do anything with them, or you can't like minimize it any further, it means that this the resultant expression is going to be your X norm of your inputs, which is A and B. Okay, And that is the same as the equality rule. When you are dealing with equality, which is A equals B, the expression is always going to be your X norm. It doesn't matter if you're having 3 inputs, and let's say you have a C, it's going to be an X norm of the 3, which is going to be A, X norm B, X norm C. So if you have A and B, then you are surely going to get an A, X norm B right here. So there is no need to even come and even do this crap. Immediately you see A equals B, you just take this as it is. Whenever you see A equals B, there is no need even coming to deduce your logic expression. A equals B, you know, is the same as A, X, no B. If it is A equals C, you know A, X, no C. Y equals Z, you should know it's Y, X, no Z. Are you together? All right, so we've already established our way forward with A equals B. And the reason why I'm highlighting this is for the sake of objectives. We are going to be working with objectives in the examination. So it's just very, very important that we're able to understand some of these way out so that if you meet anything under these areas, we are not left, I mean, please, for instance, if you are dealing with 1-bit comparator, when you are drawing your how do you call it? When you are deducing your truth table, it's much straightforward and much easier to deduce. Okay. But if you are working with something like 2-bit comparator, I'm not sure you have the time to do all those things. So you just want to understand how to go about it the easier way. Okay. And then this is an easier way to go about it. So with A greater than B, let's take greater than B. We don't have our truth table here, but let's attempt to deduce our logic expression and see if we get it correct. So let's ask ourselves the question that when would our A be greater than B? When we are dealing with zeros and ones as our A, 0 and 1 as our A and B. Please, when do you think A will be greater than B?
When A is 1 and B is 0.
When A is 1 and B is 0, that's just perfect. So in this case, you are going to get A is greater than B. And when A is 1, that is your A. When B is 0, that is B prime. You are done. So we've deduced our logic expression. Okay, and this same method is true for your 2-bit comparator. If you use the same method for your 2-bit comparator, you can be able to still determine the expression without having to do your truth table. So with this, we are going to use an AND gate, right? So with an AND gate, we have our A and then B naught. So B naught, we are going to have our B, and then we have a NOT gate right here. And then the output is A times B naught. Okay, so let's move on to less than. So A less than C, we just have to ask ourselves the same question. That when is A going to be less than B? Please, when do you think A is going to be less than B? When our inputs are 0, 1. I mean, a combination of those two. When is our A going to be less than B?
When A is 0 and B is 1.
When A is 0 and B is 1, we can see that our A will be less than B. Apart from this, if you take, let's say, A to be 1, B is 0, A is not going to be less than B. If you take 0, 0, A is not going to be less than B. If you take 1, 1, A is not going to be less than B. So, you know, A is only going to be less than B when our A is 0 and B is 1, right? So this is going to be A prime, and then we have our B, right? So A prime B. A prime B right here. If you are to represent this is an AND gate, right? So if you are to represent this we are going to have A prime, right? So we invert our A using a NOT gate, and then we have B, and the output is A prime B. So we've been able to make our deduction for our greater than or less than, and then our equality. Okay. So if we want to look at the diagram for our 1-bit comparator, we combine all the three diagrams so far. So we had this diagram, and then our equality was an XNOR gate, right? So we had something like this, which is our XNOR, and then we had B here, and then the output was an XNOR. So this was what we have. So if you bring these three together, let's draw a line here. Let's call this A. It depends on the method you want to use. If you want to use this method to draw, you can have your knots right here, A knots, and you need this is going to be A bar. Then you have your B, this is going to be B, and then you can have your B bar to do this. So for this one here, so I think let's work with the XOR first. With the XOR, we have A and B, right? So A and B, so this is our A. So we tap our first input on this point. And then we have B. B is here. So we have right here. And then we draw our XOR gates. For this, so we have A equals B here. And then the second one is A naught, so we have A prime there. And then we have B. Oh, no. Yeah, A prime is this. And then we have B. We know this is our B. And then it's an AND gate, so we have AND gate. And then we can output A. So this one was for A. I believe A less than B, right? No. That was greater than B. Not less than. So we have A greater than B. And then now let's do the last one, which is for less than. So we have A naught, which is from this point. And then we have B coming from this point. I think there's a slight mistake with this. Oh, yeah. Yeah, B naught. And then A. So here we have A naught, which is this point. And then we have B, which is right here, this point. So this is going to give us our A is less than B. So if you want to use this method, you are just good to go. Or you can decide to use the normal method to draw your logic gate diagram. Okay, that is to draw your A, draw your B, just remove with your X, or then you tap this, you invert it along the line, and just straightforward. Okay, but I think for me, I prefer doing it in this manner because it's much simpler. Okay, So please, are you all together up to this point? Okay. If there are any questions or anyone is confused with what you are doing, you can let me and I'll take that again. Because after this, I'll be
Hello,
looking at
sir.
it. Yes, please.
Please go back to the screen. Let me show you some.
Okay.
Okay. Please, the A equal B, where you took your point, can you just wrap it up for me, because it's like I can't see the point well.
Oh, okay. So A equals B. We took our first input from A, which is here. So A is here. And we took our second input from B, which is here. And then we connected it to our, because this is the original gate, which is an X node. So we connected it to our X node gates. And then we had our A equals B. Please, can you see that?
Oh, okay.
Yeah. And for A is greater than B, A is greater than B, we have our A and our B is not. So we took our A from here, from A here, and we took our B from B naught. This is B naught, so we took our B from B naught. And then for the A is less than B, we know our A was A naught, so we took our A from A naught, and then our B was B, so we took our B from. So that was where we took our increase from. To draw our diagrams.
Okay, thank you.
Yeah. So let's progress. So now let's look at a 2-bit magnitude comparator. Then we can proceed to solve some questions. I think I've put them on the platform already, but we'll go through the questions together again. So we have 2-bit magnitude comparator. Okay. So with 2-bit magnitude comparator, as I was explaining earlier, it does the same thing. That is, it compares the inputs and then returns an output. So if we have to draw a block diagram for 2-bit magnitude, it's the same, because for a magnitude comparator, it will always compare just A and B. So even in this case, we know that our variables are going to be 4, right? For a 2-bit magnitude comparator, because we are going to have, we know our bits are 2, which is, let's say, 0, 0, 0, 1, or whatever combination that might be. We are going to have A0, A1, or someone can say A1, A0. And then we are going to have B0, B1. Okay, so this A0, A1, we are going to label them as A. And this B0, B1, we are going to label them as B. So let us do them on a block diagram. So we are going to have A0 and then A1. And these are going to be just one inputs, which are going to be A. And we are going to have our B0, B1. And you can see that we've left a very huge gap between the two to signify that this is considered as 1 and this is also considered as 1. Okay, so this is going to be our B. And then the outputs are going to be in the form A equals B, A less than B, A greater than B. And here going to be our 2-bit comparator. Another way we could also draw this, which is also correct, is to take it as this. So we could have our first input, which is our A. So we could label this as A0, A1, because this is just one input. And then we label this as B0, B1. They are all correct. So our output is going to be A equals B, A less than B, A greater than B. And this is going to be a 2-bit comparator. So whichever of these two we are going to use is just the same thing. So they just mean the same thing. Okay. So now that I know the block diagram, let us look at the truth table. So to look at our truth table, we first have to determine the number of rows that we are going to use on our the number of rows that we are going to use, right? And we said to determine the number of rows, we are going to use 2 raised to the power 2n, right? So 2 raised to the power 2, and we know our n is 2. So we are going to have 2 raised to the power. And what does 2 raised to the power 4 give us? That is 16. That is 16, right? Yeah, so that's 16. So that means that we are going to have 16 rows. And you see why I was telling you that when you have the case of 2-bit comparator apples, drawing the truth table isn't something very something you want to do. Okay, so let's draw that. But for the sake of understanding, let's do that. Okay, or let's do that. So we have A1, A0, B1, we have B0. And then your first input, you know you have A equals B, A greater than B, A less than B. So now you know you are going to have 16 different rules, right? And you are going to pair your, you know, this can be 0, you start with 0, 0, 0, 0, then you go to 0, 0, 0, 1. But usually, by the time you reach 16, let me tell you this. If you make even one mistake, here man said the second is 0, 0, 0, 1. And then the third is 0, you now move to 0, 0, 1, 0, 0, 0, 1, 1. And you make a mistake, and the next one, you go and do it. Let's see, 0, 0, 0, or let's say you go and do it 1, 0, 0, 0. You've broken the pattern. And once you break the pattern, if you are to minimize using a K-map, your answer will be very wrong. Because if you are to minimize using a K-map, you are going to label the mean terms, right? Here is going to be M0, M1, M2, M3, M4, etc. And that's what you are going to use for your K-map, which is going to be very wrong. So let me show you the correct way to do that, or a very simple way to determine the correct patterns. So you are going to use usually you remember that K-map, we always, when we are selecting our mean terms, we use we use the powers of 2, right? So 2 to the power 0, right, which is 1. Then 2 to the power 1, which is 2. 2 to the power 2, which is 4. 2 to the power 3, which is 8. We said these are the number of ones that can be selected at a go. And that is the same pattern that we use to label our ones here. Okay, let's always remember that. So how do we do that? We always start with our B4, which is our last input, takes a 0, right? Please, are you all watching it? So we have 1. So at the 1 column, it means that every binary number can be repeated only once. So we have 0, 1, 0, 1, 0, 1, 0, 1. How many do we have here? 1, 2, 3, 4, 5, 6, 7, 8. We need 16, right? So 8, we have 9, 10, 11, 12, 13, 14, 15, 16. Are we together? Are you on the same page?
Yes, sir.
So far? Yes, sir. We are listening.
Besides,
Yes, sir.
yeah, please, I want to ask you a question.
Okay. We are listening.
Yeah, please, can you go to the truth table? So according to your truth table, I don't know, I'm seeing two A1s. I thought it was meant to be A1,
Oh, sorry. A1, this is A0. This is A0. Okay. This is A0. I think I intended writing A0. I think probably when I was writing A0, the 0 didn't come. Thank you for coming to me. All right, so can we progress? Please, can we progress?
Yes, sir, you can.
Okay. So now that we've labeled the last one, according to our last way, we said that we have 1, right? And 1 means that we can only repeat one binary number once. Then we come to 2. 2 means that we can repeat each binary number twice before we move to the next. So we'll take 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. I believe we've all seen how we did this. Then we come to the next one. The next one is 4. 4 means that we have to repeat each binary number 4 times before we move to the next. So 0 will come 4
So, sir,
times.
hello.
Yes, sir.
So, is it compulsory to repeat the numbers? Like, for instance, you are repeating it twice.
Okay. You said, for example, let's say writing it twice.
Yeah, for the D1.
Yeah. It's compulsory. If you might want to maybe minimize the resulting expression using a K-map, it's very compulsory that the correct pattern is maintained. Else, when you are numbering your mean terms, I wish, okay. So let's say if you have, here is 16, right? So you are going to use a 4x4 cell K-map. So you have something like this. You have something like this right here as your K-map for this, okay? So let's say you have A, B here, and then you have C, D here. You know that here is going to be your N0, right? Or if you are labeling the boxes, let me just take off the N. But here is going to be your 0, which is your N0. Here is going to be your 1, which is your mean term 1. Here is going to be 3, right? And here is going to be 2. We all understand that these 2 boxes have been changed or have been swapped. So here is going to be your 4. Here is going to be your M5. Here is going to be your M7. Here is going to be your M6 because these 2 have been swapped. So we bring 7 before 6. Here is going to be your, you don't write 8 here because you know that these 2 boxes have also been swapped. So your M8 comes here, M9, M11, then M10. Then you have your M12, M13, then you have M15, then you have M14. So you realize that the arrangement of the cells follow a particular manner and a particular order. And each one, if you write 0, 0 here, so here is 0, 0, 0, 1, then you have 1, 1, 1, 0. Then you have same thing here, 0, 0, 0, 1, you have 1, 1, you have 1, 0. Okay. So what is going to be the address of the first cell? That is going to be 0, 0, 0, 0. And that should correspond to this one exactly. So let me just complete that quickly. And then let's try to map the address, the cell addresses to the correct, thing and see if they correspond. So that means that if you see box 5, the address of box 5 should be able to map directly to row 5. I don't know if you are getting it, because we are going to label it as M0, M1, M2, M3, M4, M5. So when you get to M5 here, the address should directly match the address of M5 here. You are seeing it. Else, any resulting minimization is always going to be wrong. If you attempt to minimize this, else if you proceed to perform your minimization, it is always going to be wrong. That is why it's very important that you're able to label your combinations properly and in the correct order as well. Else it will affect the overall answer, which is your minimization. I don't know if you are getting the explanation I'm giving now. Okay, so let's finish and then we will illustrate that properly. So the third one is 4. So the 4 means that you are going to repeat each 4 times. So you have 0 repeating 4 times. So 0, 0, 0, 0, then 1, 1, 1, 1. Then you have 0, 0, 0, 0, 1, 1, 1, 1. And then the last one is 8, right? 8 means that each one is supposed to be repeated 8 times. So you repeat 0 8 times. 0, 0, 0, 0, 0, 0, 0, 0. Then you have 1 also 8 times. You have 1, 1, 1, 1, 1, 1, 1, 1. So this is how the original arrangement is supposed to be done. So if we are to perform our minimization from here using our K-map, we know here is going to be M0, here is going to be M1, here is going to be M2, here is going to be M3, here is going to be M4, here is going to be M5, right? Let me see, M0, M1, M2, M3, M4, M5. You can see that when you take M5, okay, when you take M5, which is 0, 1, 2, 3, 4, 5, when you take M5 in, you realize that the corresponding cell address or the corresponding input for that particular cell is going to be 0, 1, 0, 1, right? So let's take our 5 and let's see. If you come to our left side, our 5 is 0, 1, to the left is 0, 1. If you come and look at the top of the 5, you also have 0, 1. Please, I don't know if you've all seen that. Please, have you all seen that now? Or you are confused?
So please kindly take it again.
Okay. So I was illustrating why arranging everything in the correct order is very important, and even missing the arrangement of a line properly. Okay. All the combinations can be correct, but the arrangement is not correct, and you proceed to minimize using a K-map, the resulting answer would 100% be wrong. Okay, and I was explaining that it is because when you take K-maps, each cell is numbered intentionally, okay, to correspond with the arrangements of inputs on your truth table. Example, if you take cell 5 on your K-map, this is cell 5. What is the address of cell 5? If you look at the corresponding AB value, check cell 5 to the left. What are you going to get? It's cell 5 to the left. What is the address there for AB? Hello, are you together?
Yeah, please, I think it's 4.
Yeah, it's 0, 1, right? So 0, 1. And then the 5, if you check up there, it's also what? 0, 1. So the cell address is 0, 1, 0, 1. Okay. So if you come to your main diagram or your truth table, so if you take our truth table, so if we take our truth table and we find mean term 5, how do you find mean term 5? This is mean term 0, mean term 1, 2, 3, 4, 5. Let's look at the corresponding cell address. This is the corresponding cell address. What is it? We have the row address. I mean, you can see that that is also 0, 1, 0, 1, right? Please, can we all see that? And you can see that these two things are the same or they can. So if you do not arrange these things here properly, it will not tally with the intended positions on the K-map, which will result in a wrong minimization. Because I don't know if we are all seeing the same thing or you are confused. So I think it should be progress. Are you all okay with what you are doing so far?
Oh yeah.
Okay. Please, this is not part of it, okay? The reason why I'm indicating this or I'm trying to highlight this point is so that if in the near future you have to encounter something like this and we are drawing our truth table, okay, where we have, let's say, up to 8 rows, 16 rows or more, we have to know how to arrange our input combinations. And we should remember that we always use a ratio 8:4:2:1. Just the same ratio we use for our K-map, and that's the same ratio we use in doing our input combination. So you start from the back with 1. You know that each binary number can only repeat itself once, which is 0, then 1, then 0, then 1. So if you come to 2, each binary number will repeat itself twice. So 0011, 0011, 0011. Then you are done, you go to 4. Each binary number will be repeated 4 times, which is 0000, 1111, 0000, 1111. So you obtain a number of rows you are looking for. Then you come to 8. You know each binary number will repeat itself 8 times, like 00000000, and then 11111111. Okay, so we should just understand how to denote our input combinations. All right, so let's so now let's do our comparison. So we said that when doing the comparison, A1, A0 will only be regarded as A. This here will be regarded as A. And then B1 and B0 will be regarded as B. So here we are comparing A1, A0 to B1, B0. Okay. So we have 0, 0, and then 0, 0. As a 0, 0, and 0, 0, are they equal, greater than, or they are less than? Or one is less than the other? Okay, so we have 0, 0, and then 0, 0. Please, which symbol is true here? Please, are we together? I don't know, but the silence is quite worrying. I don't know if maybe you're caught up in something. All right, so 0, 0, you know, is equal to 0, 0. So we put our 1. And we know that for magnitude comparator, once you're able to get a high, everything else is 0. So we have 0, 0, 0, 1. You know, 0, 0 is less than 0, 0, 0, 1. So we put a 1 at less and everything else takes 0. Then we come to the next 0, 0, 1, 0. You know, 0, 0 is still less than 1, 0. So we take a 1 here. Then we put 0, 0. And then the fourth one, we have 0, 0, 1, 0. We know it's still less. So we have our 1. And then the rest takes zeros. Then we have, let me see, on 1, 2, 3, 4, 1, 2, 3, 4, on 5. So 0, 1, 0, 1. No, 0, 1, 0, 0. We know 0, 1 is greater than 0, 0, right? So we put a 1 here. Everything else takes 0. And then we come to the next. We have 0, 1. Let me see here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so we have we'll have our 1 here. Here becomes 0, 0. So you just continue to perform the comparison. So you compare these two and these two to know whether they are equal, they are greater than, or they are equal to, and you are just good to go. So here becomes 1, 0, 0. Here becomes 0, 0, 1. Here becomes 0, 0, 1. Yeah, 0, 0, 1. Here becomes 0, 1, 0. And here becomes 0. You have 0, 1, 0. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So just continue in this manner, in this fashion. So you are done with all your 16 bits, okay? And then the resultant is going to be your fruits table. So let me check how many we've done so far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. Yeah, so we just continue. So we are the last 4, right? The last person to 1, 1, 0, 0 is going to be greater. So greater will return 1, the rest takes 0. We have 1, 1, yeah, still greater takes 1, the rest takes 0. We have 1, 1, 1, 0, this greater takes 1, the rest takes 0. Then we have 1, 1, 1, 1, this takes 1. This takes 0. So that's going to be our truth table for the 2-bit magnitude comparator. So after we've gotten our truth table, We now come to look at the points where the output was 1. Okay. And then we use that to deduce our logic expression. Okay. So deducing your logic expression for equality, which is A0, B0. I mean A0, A1 being equal to B0, B1. Okay. Equality, we said equality is our X NOR gate, right? So we are going to have A0 X NOR, we are going to have a B0. Then we have another A1 B1. And that's going to be the Boolean expression for our equality right there. Okay. So you can proceed to work that out for your less than and greater than as well. So working this out for your less than and greater than. I think at this point, I don't know if there's anybody in the class. Okay. So continuing with the greater than, we are going to have A1, B1 prime, and then A1 X or B1, and A0 B all prime. This is going to be for A greater than B. And then we have A less than B. That's going to give us a similar expression. We are going to have A bar, which is A1, B1 bar. Okay. Plus we have A1, then our X or is 1, B1. Then we have A bar 0. And then I'll be 0 for this. Okay, so that's going to be our expression for A is greater than B, and then A is less than B as well. Okay, so I think at this point, I presume everyone is tired. I mean, so we can just hold the session and then continue this. All right, so we'll meet again.